Hey, what's up, guys? This is Chung here again. So let's take a look at today's daily challenge problem, which is number 1510, stone game number 4. Okay, so this is the fourth problem in the stone game theory. So again, Alice and Bob are playing a game, and with Alice starting first. So now this time they're not picking the stones. Instead, they're trying to remove the number of stones. And and the rule of removing the stone is they can only remove the stones with the square number of the stones, which means that they can only remove the stone with 1, 4, 16, right? And then 25, 36. So that's the options they can do to remove the current stone. Okay, so and it asks you to return basically a boolean to tell us if with this number of stones can Alice win the game, otherwise false. And assuming both players play optimally, right? And then it gives you a few examples here. So I mean, if you guys have seen or have done the previously stone game problems, basically this is another like stone game theory, right? Basically, one player plays first, and the other one will play the next, and assuming both players will play optimal. Okay, so for this problem, we have like, and then what's going to be the base case, right? So like this problem is telling us, right? So when the number is 0, so who is playing the DP? Basically, the DP 0 is always empty. This one is false. Okay, so it means that with 0 remainings, the player who is playing will lose the game. Okay, right? So that's why we have DP 0 equals to false. How about DP 1 here? Right, so DP 1 is true, right? Because this player can just take 1, and then the 0 will the 0 1 will be the false. That's why, because he can take 1 and to leave 0 at, I mean, the other players with false. That's why the current player will be true, right? So for the same thing, I mean, 2 is what? I think 2 is false. Yeah, 2 is false. So why is that? Because this player, remember, each player will try to play optimally. So play optimally means that as long as there is a chance for this player to win the game, he will go to that direction, right? And if all the possibility moves for this player a give him, well, I mean, will not make him win, then he has no other options but to accept his failure. For example, this one, because he only has one movement, right? He only has one movement, that's why, which is 1. That's why he'll get false, right? And then how about DP3 here? So DP3 is, I think, something like, he can also do the only movement he can do is 1. But since 2 is false, of course, so T is true, because 2 is definitely a lose, and that's why making 3 here is a win here. So for P here is 4. So for 4, what do we have? It can either go with 1, or it can just go with 4, right? So with 4 is definitely the true here, because he can just remove everything. That's why, remember, playing optimally means as long as he can win, he will go that direction, right? So now with this kind of in mind here, you guys probably can see the DP transition function here, right? So with DPI here, so this one means that, if this player can win with this stone remainings, so what's gonna be that? So if any DPK, if any DPK is false, K is what? K is from 1 to what? 1 to 1 to the square root of I, right? And probably plus 1, something like this, because that's the only thing he can, right? He can go, and then we'll return true for this one, otherwise false. Yeah, I think that's it. That's the basic state transition function for this problem. And then so with that, we can simply use either top down or bottom up. Let's try top down here. So this top down is pretty straightforward. We have our current, right? The current is like this, and then we simply return the dpn. Okay, I'm gonna use like a, a trick here to help us do the caching here for the top down, so that we don't need to write that, the memorization stuff. Like I said, so if the current one is 0, and then it means that, okay, so this one is definitely a loose, which is going to be returning false. Otherwise, right? Otherwise, how are we going to check the current one? The current one is for I in the range of what? From 1 to int of the square root of the current, and we do a plus 1. That basically that's the range we can. That's basically the all the possible stones we can take with the remaining one, right? And among all those possibilities, as long as if there is like a dp after taking this I, we have I 2, right? That's the remaining stones. As long as there's like a state that can make the other person a lose, we will go to that direction, which means we find a winning strategy, right? And then we return true here. Otherwise, there's if if there's no way the current one, any of the strategy will make us a win. So like I said, we have to admit our failure here, accept our failure, which means we'll return false with the current one, right? And as you can see, that's why we can simply return the n here. So return n means that, with the current n, can we win or not? Basically, this one is always telling us a true or false. And with the current state, we can use the previously state or the next state to telling us if we can find a guaranteed winning strategy, right, for the current number here. Yeah. So that's that. We can run the code here, submit. Yeah, cool. So it's accepted, right? So about time and space complexity, right? So the time complexity is the in total we're gonna have like we will have like in total O of n calls here, and for each of the O of n call, and we'll do it like this, right? So this is gonna be what? It's gonna be a O of n times, yes, n to the 1.5, right? The power of 1.5, which is the n times square n, something like this, right? That's going to be the space time complexity. And space complexity, this is the time. Space complexity is the O of n. That's the number of the dp cost. Okay, so that's that. Okay, it's pretty straightforward, right? So I'll just quickly write the bottom up. So for bottom up, it's pretty straightforward. So similar idea here. So we're gonna initialize with everything with n plus 1 here. Okay. So again, so for the top down, right? So from current state, we're trying to go to the next state, and we're getting the result from the next state with the base case. And for the bottom up, right? What we're doing here is we are like looking we're looking backwards, right? We're looking back basically, So with the current DPI here, how can we determine if the current DPI is true or false? Similar as this one. Okay, since we know the DP0 is false, right? So we know the DP0 is false. All we need to do is just like we're just using the same formula here. So we need to have a k here. I think in the range of I'm going to copy this thing here, right? So square I here. So basically at the current with the current I here, can we find any previously state that is a guaranteed lose for the other person, right? So that if this dpi is the dpi minus k to the power of square 2, right? To the power of 2 is a false. Okay, then we know, okay, since this state can make the other person a definitely lose, we'll just go with that route, right? So basically, we'll simply set this one to true. I mean, if none of this works, basically it will stay as false since we are setting everything at false first, right? And then in the end, we simply return the DPN. Okay. Yeah, here we're starting at stone 1 because for stone 0 we already know the answer, right? That's why we just start from 1 here. Yeah, I'll just run this. Yeah, I don't know why it's taking that long. Let me submit it one more time here. Hmm. Oh, sorry, I think I know why. Because we forgot to break it. That's why it's so slow here. Okay. Yeah, so now it's much faster because like since we already find a winning strategy, there's no point to try other scenarios, right? Because as long as we know there's a winning strategy, can guarantee us a win, we'll definitely go with that. So that's that. And as you guys can see here, right? So here, so this one is the top down, okay, and this one is the bottom up, right? So as you guys can see, the top down use a lot of much more memory than the bottom up, even though they have a similar running time here. So why is that? This is because they will need more space to store the status, or the callback information for each of the recursive call here. While in the bottom up solutions, all we need is this DP array, which is the O of n, the space, right? So that's the everything we need. Actually, even though in the top down, in theory it's O of n, but in the reality it's much more. It's much more than the O of n, because we didn't count the space we need to keep the state of each of the recursive call. That's why if we can use like a bottom up, try to use a bottom up because it's much more space efficient. You know. Okay, so as you guys can see, this is uh much clearer, right? So the space time complexity, we have on here, and later on here we have like what times o. We have n times here, right? Square of n. Cool. Yeah, I think that's it for this problem. It's a pretty straightforward problem. The only the only difficulty for this problem is that you just have to be able to understand the the concept of this game theory. I highly recommend you guys try to solve the other three stone game problems, even though those three problems are for different uh, strategy and will have a use a different solutions. Yeah, but it's worth doing. It will help you understand the game theories. What does this kind of play optimal means, right? And as for this problem is that as long as we have a winning point, a winning strategy, we'll go with that. And otherwise, we have to accept our failure, and we'll repeatedly use this one to help us to determine if this current player can win or not, right? By looping through all our options here. Cool. I think that's it for this problem. Thank you so much, guys, for watching this video. Stay tuned. See you guys soon. Bye bye.